Hello Year 12 and welcome to the second part of our first projectile motion exercise. We're going to extend on some of those ideas from the first video there, and we're going to look at a case here where we have an unknown angle. Rightio, so in this example, from the origin, we're firing a projectile with an initial speed of 200 meters per second. G is equal to negative 10 meters per second squared, and we're aiming to hit a point that is 2 kilometers horizontally and 1,000 meters or 1 kilometer vertically away. Righto. So we're trying to hit this point that's across and up, and I need to find the correct angle of inclination, right? The initial angle of inclination, so that I can hit that point. There will be two answers, right? Let's have a look here. We can kind of see a pretty rough sketch here of a mountain that is 2 kilometers wide and 1 kilometer high, or 2,000 meters, 1,000 meters. Essentially, I'm trying to hit the point that has coordinates 2,000, 1,000. I know my initial speed, and I need to find the angle of inclination. So we can have a look here, maybe, right? We can see there's one of my angles, right? And I can travel up and down and hit the point there with that angle. And there's another lower angle, oh, here we go, just there, and again with the same initial speed but a different angle of inclination, I'll hit the point that way as well, but I need to find those two angles. So we first develop our equations of motion. First up, our horizontal acceleration equals 0, as it always is. Our initial velocity, our horizontal velocity is the integral of that, is some constant, and it's 200 cos alpha, where alpha is going to be our angle of inclination. I don't know what alpha is at this stage, and I'm expecting to get two different answers for alpha. So all I've got now is that expression there, 200 cos alpha. I could do that substitution plus a constant, but oh no, that is my constant. Sorry, there's my constant. My displacement, my horizontal displacement, is the integral of that, so it's 200t cos alpha plus some constant, but of course my initial position is 0. So when t equals 0, x equals 0, substituting that into my equation, I find that c2 equals 0. So my horizontal displacement equation is x equals 200t cos alpha. So in red, I highlighted there my three horizontal motion equations. Now we did the same with vertical. My vertical acceleration is negative 10 as provided by the question. So the integral of that is negative 10t plus a new constant. Substituting in my initial values, when t equals 0, my vertical velocity is 200 sine alpha. Not knowing what alpha is at this stage. So substituting t equals 0, y dot equals 200 sine alpha, I find that c3 equals 200 sine alpha. So my fifth equation of motion is y dot equals negative 10t plus 200 sine alpha. Integrating that, I get y equals negative 5t squared plus 200t sine alpha plus another constant. And substituting t equals 0, y equals 0, because we're starting from the origin, then we find that our c4 there, that constant, is equal to 0. So my final equation of motion there is y equals negative 5t squared plus 200t sine alpha. There's my 6 equations of motion. I'm going to take the four most important ones of those, my velocity and displacement, and just leave them up the top of my page so I can refer to them as we go through the working here. So I've got my equations of motion. What I need to find now is when I'm going to hit that target at point F, right, with coordinates 2,000, 1,000. So I'm going to substitute x equals 2,000 into my horizontal displacement equation, right? So there's my horizontal displacement equation. X equals 2,000. Replace the x with a 2,000. we get this equation here, dividing through by 200 cos alpha, I get t equals 2000 on 200 cos alpha, which simplifies pretty easily to t equals 10 over cos alpha, right? T equals 10 over cos alpha. That is the time at which my impact will occur. We do a similar thing now where we say that let y equal 1000, because again my impact will occur when y equals 1000. So we substitute into my vertical displacement equation, right? Replace y with 1000, and we get that equation there. Now, from there, I don't really want to make t the subject again. That's not going to be terribly helpful. What I'm going to do is substitute in the value for t that we found from our horizontal displacement equation. Right, so we're going to remove the parameter here, and we're going to end up with an equation solely in terms of alpha. Okay, so I replace the t with 10 over cos alpha. We get this thing here, we expand it out a little bit. Now, because 1 over cos is sec, I've written instead of negative 500 over cos squared alpha, I've said negative 500 sec squared alpha. Okay, and other than that, it should follow along reasonably well. We subtracted 1000 from both sides as well to get everything on the same side of the equals. Now, from there, so how am I going to solve that in terms of sec squared alpha and tan alpha? Well, if we come to our our Pythagorean identity, cos squared plus sine squared equals 1, divide both sides by cos squared over cos squared is plus sine squared over cos squared equals 1 over cos squared. Now 1 over cos squared is sec squared, cos squared over cos squared is 1, sine squared over cos squared is tan. I forgot to mention we introduced that tan because I had a sine over cos in one of those terms as well, sorry. So that's just a little reminder there. It's in green. You really don't have to show that working. You very reasonably remember that identity. I don't necessarily, but I do remember how we arrive at it. So I'm going to replace my sec squared now with 1 plus tan squared. Right, swap over the sec squared with 1 plus tan squared, expand that out, tidy it up a little more. We get negative 500 tan squared alpha plus 2000 tan alpha minus 1500 equals 0. I've got a big common factor of negative 500. I'm going to divide both sides by negative 500 to give us a much neater equation here of tan squared alpha minus 4 tan alpha plus 3 equals 0. We've got a quadratic in terms of tan alpha, and I'm looking for numbers that multiply to give me 3 and add to give me negative 4, so that's negative 3 and negative 1, which means that tan alpha equals 1 or 3, which means that alpha is the inverse tan of 1 or the inverse tan of 3. The inverse tan of 1 is exactly 45 degrees. The inverse tan of 3 is approximately 71 degrees 34 minutes. That's my answer. What are the two angles? Those are my two angles. So if we fire that gun at either 45 degrees or 71 degrees 34 minutes, we should hit that point. That is 2 kilometers across and 1,000 meters up. Righto, that's it. Now that problem gets a lot messier, as we've seen in class, where the equation there in terms of tan squared and tan alpha, where that doesn't factorize as neatly as negative 1, negative 3. Right? If that doesn't factorize neatly, we've got to use the quadratic equation or the quadratic formula to arrive at those things. That gets a bit scrappy, but nonetheless, it's a reasonable process. It's just the numbers get a bit unwieldy at times, so we can do that. Another question that we haven't looked at is I could give you the initial angle of inclination, but not tell you the initial speed. It's not as practical a problem, but nonetheless, we could have that, and we could solve for that initial speed as well if we are given a point of impact. Rightio, that's it for the second part of 10A. Next up, 10B, and that's relatively straightforward. We'll have a look at that next. Okay, if you've got any questions, make sure you let me know. Otherwise, I'll see you in class.